Hello student, to the foundation of classical electrodynamics course. Under module 3, today we have lecture 57 and we will continue our discussion on magnetic dipole moment in this class also. So, we have class number 57. So, we already mentioned that the magnetic dipole moment M is defined like half of I, this is one way, integral r cross dl, and also it can be defined as half then integral r cross j r prime dl prime, sorry dv, because I am using the volume current. So, it should not be L, it should be V. Okay. So, now today we will, so with that note, today what we do is try to understand the orbital and spin magnetic moment. Orbital and spin magnetic moment is important in atomic and molecular physics. So, this is a very important physical concept. To try to understand that these here in the light of electrodynamical theories. So, what we have here is, if a particle having charge, suppose if a particle having charge say qk, discrete particle, so charge qk, and velocity say v k vector, which is d r k dt, charge q and velocity v k, and also mass say m k. Okay. The associated current density, if that is the case, so if a charged particle q is there and then the velocity is this and mass is m k. Now, if there are many particles, not one particle, but there are many particles that is flowing, discrete particles, this discrete charged particle with mass m is flowing. So, suppose I have this one charged particle, this another charged particle, this another. So, these are the charged particles and they are in motion. All are moving, and these is q k, the charge, mass is m k, kth particle mass is m k, and velocity is v k. These are given for all the particles 1, 2, 3, 4, 1, 2, 3, 4, etc. And for kth particle, these are the thing. Now, the current density, if they are flowing, then the corresponding current density, if I want to write J, and we know that for discrete charge that is moving, the current density can be written in terms of in terms of delta functions, like the way we write the the volume charge density for a discrete charge. Here they are moving, so I am writing the current charge the current density for these discrete charges. So, it should be q k and then v k vector and then delta r minus r k, because for if they are in stationary state, then the rho is that quantity q k and delta r minus r k. That was the value of the charge volume charge density for discrete charge, and now I write the current density for this discrete charge, which is moving with a velocity v k different. So, the magnetic moment, already I mentioned that the magnetic moment is half then integral r cross j and then the function of r prime and dv prime in terms of, this is a general form in terms of current density. So, exploiting the value of the j here, what we had, I can write my m, let me write it here, m now is half of integral r prime and then cross, and j is the summation of all these charged particle over k, and then we have q k and then we have v k and delta r prime minus r k and over dv prime. So, this integral is over dv prime and delta function is associated with that. So, that simply reduces the equation, and I can simply have half of the summation. I put this integral inside and it should be k, say from 1 to n number of particles, say n, then q k and then this will be r k cross v k. So, that should be the magnetic moment. Now, the angular moment can be represented like L k, the kth particle angular momentum is m k r k cross v k. So, that means I can write my magnetic moment in terms of this angular moment. So, magnetic moment now, if m is simply sum over k from 1 to number of particle n q k divided by m k and the rest of the term 2 m k, because half is there, and the rest of the term is L k. And now, if all the particles have the same charge to mass ratio, so all the particles, if all the particles have the same charge to mass ratio. Then we simply have ml as q by 2 m sum over k l. I can take this q by m outside this integral because, and then it should be simply q by 2 m angular momentum L. So, so this is the relationship with the magnetic moment with the angular moment, the relationship with the magnetic moment with the angular moment. And for quantum particle with quantum particle, with spin angular moment angular momentum so this is the angular momentum with the spin angular momentum, say S, the vector S. The intrinsic, so that spin angular momentum can produce an intrinsic spin magnetic moment. So, that intrinsic spin magnetic moment can be defined as the spin magnetic moment is equal to q divided by 2 m s like before, but we have a factor here, very important factor g, and that is called the dimension, this is called the dimension correction factor or g factor. This is a dimensionless correction factor. Or G factor. So, this is the, I mean, just to in this treatment just to show that how one can correlate with the magnetic moment with the spin angular momentum or spin angular linear angular momentum or spin angular momentum. So, this is the way one can correlate that. Now, after that we will proceed further. So, one thing I missed in the last class, so let me write here the magnetic field due to dipole. So, we know that whenever we have a tiny, so current loop is essentially, so this is the current loop, and this current loop can produce a vector field here, and the dipole contribution, if I write, that is the first important contribution, because monopole is not there in case of magnetic field. So, this current loop which behave like a dipole can produce a potential here, scalar vector potential, which we call the magnetic vector potential with the dipole contribution. So, this magnetic, now this dipole potential can give rise to some magnetic field. So, here we try to understand the magnetic field give rise to the magnetic field due to the dipole. Dipole here means magnetic dipole. So, how I get that? So, B R, this is the magnetic field that is supposed to produce due to the magnetic dipole. So, I should write as A dip. So, that is mu 0 divided by 4 pi, and I now have here, so 3 R and then 3 unit vector R. I am just writing the result here. This is a homework for you. I like to give this as a homework because the same problem that was okay. This is the vector sign. A similar problem for electrostatic we had, if you remember, exactly the same expression one can get. So, divided by R cube. Okay. So, the A dipole we know what is A dipole. A dipole is, say, this is the dipole contribution one can have for, you know, for this this magnetic. So, it is mu 0 what we extracted last day, 4 pi r square, and then we have m cross r. Now, if I want to find out B, then you just need to make a curl of both sides and check that whether you are getting this result or not. You just need to make curl of both sides and try to figure out whether you are getting this result or not. This is a straightforward exercise, and I hope you can do that. But the thing that I like to, so here M is the magnetic dipole moment. Magnetic dipole moment. Now, for electric field, what we got, let me remind. For electric field in electrostatic, E was minus of grad phi, and for dipole we had the dipole potential and the electric field due to dipole, the electric field due to electric dipole, that was 1 by 4 pi epsilon naught, and the term here was exactly same except the magnetic dipole. Here we have the electric dipole. So, P dot R minus R P, I should have a vector sign here. Let me erase this. Whole divided by R square, sorry, whole divided by R cube. Because I am calculating electric field, R cube. So, here you can see only the M is replaced by P here for So, here P is the electric dipole moment. Since the expressions are very similar, so you should note that the expression are almost identical. So, note B for, so what happened, B R for a point dipole, point magnetic dipole, has exactly the same pattern of field lines as E R for point electric dipole. So, what does it means that since the expression of B and M are very much identical, so the field line that due to the magnetic dipole, the magnetic field that is produced due to the magnetic dipole should be identical to the electric field that is produced for the point electric dipole, because the expressions are very much same, that you need to remember. Okay. After that, the thing that we do today is this, like in electrostatic case, we place the electric dipole in an external electric field. Here we will do characteristically a similar thing, that we place the magnetic dipole, that is a current loop, in an external magnetic field. So, current loop which gives rise to a magnetic dipole moment is placed in an external magnetic field. And so, I placed a current loop in external magnetic field. Now, so first we need to find out the force. The force on a current element. So, if I have a current element ideal, so okay, so let us have a loop here. Say this is my current loop, some current is flowing I, and we have so this is a vector R, and here it is dl vector. So, the force on the this current element is dF is equal to the current element that we are having cross the external magnetic field. That is the force that one can have. So, I have an external magnetic field here in some direction, and that will produce some kind of force here in this current element, dl. Now, the torque on the planar current loop this is the force, the torque on the planar current loop is N equal to R cross dF. This is the torque one can have. So, that eventually gives me R cross dF I already defined here. So, it is I dl then cross B. Okay, from here you can note one thing. So, dl is nothing but dr, because I am writing, so this is equivalent, right. So, it will be easier for me because this is r and this is r plus dr. So, dl should be equivalent to dr. So, now what we do is this. If I, so this is my torque. So, d of r cross B, if I want to calculate this quantity, it should be dr cross r cross B plus r cross dr cross B. B is a constant. So, and also this is a closed integral. If I make a closed integral of this quantity, which is a complete integral, so r cross B, it will simply gives me 0, because the we are calculating the loop integral of a perfect differential. So, this is the loop integral and we had integrate a perfect differential. So, this has to be 0. So, let me comment here the loop integral or the closed line integral of a perfect differential is 0. Okay. So, that quantity should be 0. Now, if that is the case, then we can exploit this to find the relation that dr cross r cross B is equal to minus of B. Now, once we have this, let us go back to the expression of the n that we figured. So, n is equal to I closed line integral. So, what was that? N was n was I closed line integral here. Then I can take I outside and dl is dr. So, So, from here I can write is n is equal to r cross dr cross b. So, r cross dr cross b is from the okay. Now, let us manipulate this. So, we know that A cross, this is a cyclic rule, B cross C plus B cross C cross A plus C cross A cross B is 0. So, I can write as R cross dr cross B dr cross B plus dr cross B cross R plus B cross R cross dr is equal to 0. So, I can have the closed line integral R cross dr cross B is equal to closed line integral R cross dr cross B minus. So, here okay. So, dr cross R cross B. So, that basically gives me this quantity as 2 of integral R cross dr cross B. Because from here I just write it as R cross dr cross B, and that should be a negative sign. So, that makes it plus, and then we have this. So, just we exploit the expression that is here, and I can have dr cross B cross R is equal to R cross dr cross B. If I go this side, it should be negative sign, and I am going to get this. So, what I finally have is this one, that R cross dr cross B is equal to half of R cross dr cross B. So, n is eventually, so what was the value of the n, that is R cross. So, I can put I outside. So, here n is simply the torque is I divided by 2, and then close integral, then we have R cross dr cross B. So, B is constant here, you should note. So the point here is to write in these things in r cross dr to get the feeling of the magnetic potential, magnetic moment, magnetic dipole moment. So, I can write this half of I integral r cross dr, bracket it, and then we have cross B. So, this quantity is m. So, I simply have m cross B. So, the point of this entire calculation is to find out the amount of torque that a current loop will going to experience in terms of the magnetic dipole moment m and the external field, external magnetic field B. And simply, so this calculation looks little bit clumsy, but if you go to step by step, I think you will understand. So, let me go back and check once again. So, N is simply the R cross the force that we are going to experience by this loop. The current element is I dl cross B, the I dl, and the force that we are going to experience by the magnetic field is this cross B. So, this is q v cross B. So, I can write q v is in terms of current and dl. So, it is the current element cross B. So, in the torque should be r cross df. Df I just replace here I dl, and then I can take this I outside because I is a steady current that is flowing. So, eventually I have I. So, this things is simply I, and then I have closed line integral of r cross, and then I have dl, I replace dr for my convenience because these are two same things, cross B. The next part was to just write r cross dr cross B in terms of r cross, the last line what I get r cross dr cross B. So, I just use a few we just use few vector identities, like d of these things is this quantity. So, if I make a closed line integral, so I have, so r cross B should be minus of r cross dr cross B. So, that we use here, and I put this inside. So, whatever the value we had here, r cross dr cross B, I just then use the A cross B cross C plus B cross C cross A plus C cross A cross B equal to 0, and then just replace A, B, C in terms of R, dr and B, and carry forward the calculation. When you carry forward the calculation, we find that R cross dr cross B can be represented in terms of R cross dr cross B with twice of that. So, R cross dr cross B is now half of this quantity, and then I replace this R cross dr cross B from here. So, this R cross dr cross B is finally replaced here, R cross with the half of R cross dr cross B, and eventually we find our magnetic dipole moment. So, my torque becomes the magnetic dipole moment cross the amount of magnetic field that is there. So, when the loop is there, so I know what is the magnetic moment, and if the B is known and the magnetic moment is known, which is current into area. So, that is the amount of the torque it will going to experience under the external magnetic field. So, please check this calculation and try to do that. So, and I believe you can understand this. It is just we are just using some vector identities, some mathematical juggleries are there, but at the end of the day you will going to get the result quite straightforward results. So, with that note, I think I should conclude here in today's class. So, I think in the next class I will like to discuss about the magnetostatic in magnetization problem. That means inside a magnetic system, if I apply the magnetic field and if I put a magnetic system, the magnetization will be there, and how this magnetization can be calculated, what should be the physical significance, how physically we can calculate all these aspects, we will going to discuss. It is exactly same like putting a dielectric field, putting a dielectric material in an external electric field and how the polarization appears. So, here in terms of magnetic field we have magnetization, and how the magnetization can be represented in terms of this magnetic dipole moment, etc., we will going to discuss. So, thank you for your attention and see you in the next class.